So this is the second video I wanted to do based on some of the questions I was getting on Friday. And it's kind of a tricky concept, so I thought we'd just take some time and go through an example with electric fields. Electric fields. And the first question I get is, why do we treat it like a positive probe charge when we're looking at the electric field at some location related to the source charge that's creating the field? And first, let's make sure that we remind ourselves that the electric field is defined in terms of the electrostatic constant, the charge creating that field, divided by the distance away from that charge squared. So the r squared, that still stays the same, but now we're not looking at two charges interacting. That would be a force. We're looking at a charge creating an electric field. Okay. But the question was, why, I just derailed myself, why do we treat the test probe charge as positive? And I just want to remind you real quick that, remember when we defined our electric fields, we said our electric fields emanate out from a positive charge, like so, and into a negative charge. So the reason we define our test probe charge as being positive is because that probe charge in the field of a positive or negative will be in the direction that we've defined that field. So if I take or we'll move in the direction of that, how we've defined that field. So if I take a positive charge here and put it next to this other positive charge, well, which way is it going to go? It's going to be repulsed. So its motion would be that way. It's going to move in the direction of the electric field, is the way to think about that. So it's going to go that way. Well, that's in the same line as how I've defined that the electric field comes out of a positive and into a negative. Because we'll do the same thing here. If I put a positive charge here, what direction is it going to go because of that negative charge? Well, it's going to go towards it, which is in the same direction as how we've defined electric fields. And I know this gets somewhat confusing because we went back to kind of the history of things and they thought it was positive charges moving, and that's why things aren't quite as intuitive to you as they might be. But I just really need you to trust me on this. The math is going to come out exactly the same, and everything that we've defined out of or into, those are things that were defined when it was first discovered that the behavior existed. So what is positive and what is negative is really arbitrary anyhow. It's just how we define those things. Now let's go back to our electric fields. The question that I had on the quiz was, if I want to know what direction and the magnitude of the electric field related to these two charges at the origin. And you're given some distance. You're told that, like, I don't know, I'm going to pick pretty numbers because I want to. So I'm told that, like, this is 2 meters and this is, like, I don't know, 3 meters. Let's just do something different. So we know that the height on the y-axis is 3 and that this charge is over here on the 2. What we want to do is take one charge at a time. So first let's solve this like we want the whole net field, not just like we want one component. But we're going to take one charge at a time. So I'm going to like pretend that the one that's on the x-axis isn't there and only focus on the top. And first let's give these charge values. So let's call this one, oops, that's not what I wanted. I'm going to call this top charge positive. I don't even remember what the quiz question was, but we'll call it like positive 3 nanocoulombs. And this one we'll call like negative 5 nanocoulombs. Why not? When I focus on just one, I'm going to ask myself in a straight line distance, what is my positive test charge going to do with respect to whichever one I'm looking at? So I'm going to start with the positive 3. And if I look at it at the origin, what direction is it going to go from the 3? Well, it's going to be repelled from because they're both positive. So I can kind of do this thing, and I'm going to try to do my best to do a straight line. It's going to pass right through the origin, and it's going to go off that way. Whoop, there we go. Hey, look at that. That's so pretty. So this would be the electric field from the 3 nanocoulomb. So the 3C, I'll just call it. What that one is at an angle. So what we've actually drawn is the resultant electric field. We don't have that in components yet. And why is that important? Well, because now when I look at, let's choose a different color. Now when I look at that negative charge, well, what's going to happen with respect to the negative charge? Well, my positive charge is going to be attracted to the negative. So I have that straight line attraction, and this would be the E field with respect to the 5 Coulomb charge. So let's bring it down here so we can see it. I'm going to have, this would be my E from the 3, and this would be my E from the 5. Cool. So just like our forces, these things stay the same as we've been doing them. We need to, now let's draw on an axis. Bonk, bonk. Here's my axes. I'm going to stick with up and to the right as positive. Just like with forces, these are vector quantities, so I'm going to sum in my x and my y. So my E in the x, well, what do I have here? I should do the sum of E in the x. I have my 5 Coulomb charge going to the right, which I've defined as positive. So I'm going to have this, I'll just put the positive sign there just to reinforce that. I have the positive electric field from the 5 nanocoulomb charge. And then I have an x component from this 3 nanocoulomb charge. So its x component is coming out like this, and then a y component coming down like that, EY. Make sure that's clear. That's an x. So just like our forces from last quarter, then I need to break this thing, this 3, into angles so I can work with them. So there's my E for my 5 plus, oops, sorry, minus, because it's going in the negative direction. And what I've defined is a negative direction. So minus, let's see, if I'm choosing this angle here, the E and the X is touching, so I would be E, and this is my 3 Coulomb charge, and times cosine of this angle theta. Cosine of theta. I'm looking for my net electric field, so this is just going to equal whatever that sum is, and that will give me my net electric field in the x hat, or I hat, however you want to write it. Now I can look in terms of the sum of my electric fields in the y. Well, this is kind of nice because I only have this y component. The charge that's on the axes doesn't have a y piece, so the only electric field is related to the 3 Coulomb charge. So let's see, that's going down. So that gets a negative sign. It's below the axes and going down. And let's see, what do we have? We have E3, and if I'm using that angle, that's going to be times sine of theta. That will equal my E in the y. Now I want to talk about something that melts people's brains, because the most common thing I see, and we're going to step it up in the next lecture video, so let's tackle this now, is that you look at this vector and you say to me, we don't know how long it is. How can I possibly add vectors together if I don't know the length? Or if I don't know the length, how do I know the angles? What is true about these vectors is because they are staying in the line. So starting here and coming on through here, it's a straight line shot. That means I know something about these angles. I know what this angle is going to equal this angle, alternating angles. So the proportionality will hold. The lengths of the x and the y will change. If the proportionality holds, then that tells me that I can use these sides here to figure out what the angle is. And I'm going to need those sides to figure out what my r is anyhow. So I can look at this, I can start here, and let's define what our r is. Our r is going to be, let's see, 2 squared plus 3 squared. That's going to give me my distance away. Now to get this angle here, I can use any trig function I want. It doesn't matter. In fact, if I wanted to define this angle instead, I could go for it. That's totally fine. I'm going to get the same answer. So don't like fixate on it needing to be some specific angle. You're going to get the same answer. Trust me. So I'm going to use this one because that's how I chose to do my breakdowns for my vector components. And if I look at that one, let's see, let's go, I don't know, tan theta. So tan theta equals, let's see, opposite, so the 3 meters over adjacent 2 meters. Units cancel, which is good. So arctan of 3/2 would tell me what this theta is. This theta and this theta. I can put those values in, and now I have actual numeric values for both of those components. So in the quiz question, there was 2 things that went wrong with it. The book had the wrong sign. It is indeed a negative sign. And I think they had the exponent to a negative value, and it should have been positive. But this is absolutely, the approach is not changing at all. And so after this, we're going to step it up a bit and add a little bit more complexity to it.